Welcome back. In today's lecture, I am going to continue whatever we have learned so far. Okay, in previous class, I have started unconstrained optimization. Okay, and what we have seen that whenever I have some kind of real valued function, because I am just talking about finite dimensional optimization problem. So I have taken this function and I am assuming that is mapping from Rn to R, and now I have to minimize this function, and I have already told you that I am just going to solve the minimization problem. Maximization is obvious, just you have to put the negative sign here. Okay, so I am going to minimize this function, and what we found that if x star is the minimum of this function fx, at that time I have some condition, and in order to find that condition, what I have done, first I can express this fx in terms of some other scalar function g alpha, and I have defined g alpha like f x star alpha and d. Okay, and after that I am assuming that alpha belongs to some kind of real number and d obviously belongs to Rn. Okay, and what we found that if I substitute alpha equal to 0, at that time g0 equal to fx star. It means that g0 is nothing but the minima of, either you can calculate minima fx star or g0, both are exactly the same. Okay, and one more condition I have actually derived using Taylor series expansion of this function about alpha equal to 0, because now we know that alpha equal to 0 is the minima of g alpha, and what we have actually seen that during the first order approximation I am assuming that all term which of the higher order, that is less dominated than the first order term. Okay, and after that I land up to this expression that g dash equal to 0, g dash 0 equal to 0 if I have some kind of minima that occur for this function, and after that I have expressed same kind of things with respect to original function. I have taken the derivative. Okay, and since now fx, here you can see that x belongs to Rn, so whenever I am going to take the derivative of f, then I have to take derivative with respect to x1, x2 and xn. So you can actually define like this: f x x1 up to xn I have, and after that since I have function with respect to x1, x2, x3 like that, due to that reason gradient is involved here, and after that just by chain rule you can see that this is dot product and d, or inner product, you can tell inner product and d. Okay, and after that I have retained same kind of things in shorter notion like this, and finally what I am going to do, that I am going to substitute alpha equal to 0 and going to substitute that kind of condition g dash equal to 0. Then since d is arbitrary, so I can tell that okay, if this condition is satisfied, then x star, this particular point is the optimal point. Okay, or some kind of minimum or maximum point. So here I have extended this using minima, due to that reason I am telling that is a minimum point, but if you put negative sign, again everything remains the same. Okay, so due to that reason x star may be minima and maxima, that is depending on the situation, and this is called first order necessary condition for optimality. And in the previous class I have already talked that why I am telling this is first order. because this condition we have derived using the Taylor series expansion of g alpha function about alpha equal to 0. Okay, and after that what I am going to assume that this term is going to dominate over higher order term. So based on this assumption, I have derived this kind of criteria that this as a stationary point. And now in order to solve this kind of problem, we are always assume that function is continuously differentiable at least one time. Okay, could you please tell me that why this assumption is required? Anyone? Priyanka, could you please comment why this assumption is required? You are muted.
Yes, which one, sir? F belongs to C inverse.
Yeah, continuously differentiable function. Why the means f should be continuously differentiable?
Sir, due to the Taylor series
Yeah,
basis
Taylor series. In
functions.
order to existence of Taylor series expansion, I need this kind of condition. Okay, now what I am going to do, I am going to derive another necessary condition. Okay, so this is necessary condition. Why this is necessary condition? Iram, could you please comment about that? Iram?
Uh, yes, sir. It is necessary because if it is satisfied, then the result is or means that the result is also true if
Yeah.
this condition is
And
satisfied.
if this is not satisfied, then what happens?
Then the result is not true.
Okay. Now what I am going to do, I am going to find the second necessary condition. Okay. Similar like first necessary condition, and here whenever I am going to talk about second necessary condition, I am going to actually make a stronger hypothesis. It means that I am going to take some kind of assumption that is more strict. Okay, what I am going to assume that I am going to extremize those kind of function or minimize those kind of function that is two time differentiable. Okay, and after that what I am going to do now, I am assuming that whatever first order necessary condition that is satisfied. So what does it mean? First order necessary condition will satisfy means g dash 0 equal to 0. So that kind of condition I am telling. So under this particular assumption that first order condition holds and x star is the minimum, because I am talking about x star of this function. So corresponding mapping is nothing but g0. Anyone has confusion? Because I have defined g alpha, that is f x plus alpha x star into d. Due to that reason I am telling. Okay, so same thing I have written here. First we assume before that x star is local minimum. Okay, and similarly you can derive same kind of result for the local maximum. Okay, and derive a necessary condition. Okay, so what I am going to do now, I am going to perform the Taylor series expansion, and I know that function fx is two time differentiable, and with help of fx I have defined g alpha, and due to that reason I can automatically assume that g also two time differentiable. Okay, and after that I have done this kind of Taylor series expansion. In previous class I have explained why Taylor series, how to write Taylor series expansion. Even if I don't remember it, I have told you that you can choose the basis is 1 alpha alpha square alpha cube like that. Okay, and after that you can write some function as the linear combination of that. Okay, So I have written G alpha, that is linear combination of C, basis is 1, C2 basis is alpha, C3 basis is alpha squared, like that. Okay, so if you know the basis of some function, then you are able to calculate C1, C2, C3. And in order to calculate C1, C2, C3, I am going to use the assumption that G alpha is infinite many time differentiable. Here I am just concentrated up to second order term, and due to that reason I am assuming that at least 2 time differentiable. Okay, and whatever higher order term, I am assuming that that is less dominant than this particular term. Okay, so this particular assumption is telling the same, that as alpha is very small, at that time limit of this term O alpha square by alpha square, that is equal to 0. It means that mathematically I can also tell that there exists a epsilon, and if alpha is less than epsilon, then this kind of condition is satisfied. Okay, anyone has confusion? Now what basically we are going to show now in today's lecture, that second order necessary condition is like this. I can write that double derivative of g about 0, that is greater than 0. Okay, that I am going to establish, and in order to establish this I am going to assume that first order necessary condition is satisfied. So most of time whenever we are trying to establish this kind of relationship, one usual way to prove it, you can prove by contradiction. Okay, so what I am going to do, I am telling that g dash greater than 0. So in order to contradict this, I am going to assume the reverse of this. Okay, so I am assuming g dash 0 less than equal to 0. Okay, since equality is included here, due to that reason I have excluded from here. Okay, now you assuming this, I am going to create some kind of contradiction. Okay, that minima is not hold if this kind of condition is satisfied. So obviously this will true, like that I am going to prove. Okay, so what we have seen, that second order Taylor series expansion of this can be written like this, and after that I know that g dash 0 is 0. Due to that reason this term is not here. After that I am assuming that this term, higher order term, that is tending towards 0. If alpha tending towards 0, then that equal to 0. So equivalently I can also able to express using the epsilon condition, that if alpha is very remains in some epsilon ball very near to the epsilon, or very small quantity, then this relation will satisfy. Okay, now since g double dash 0 is less than 0, so you can see from here that this term is negative. Obviously this term I cannot tell that that is negative or positive, but I know that this term is going to dominate over this term by this relationship, and due to that reason this term, whole term from here to here, is obviously negative. Okay, so negative means since this is 0, so if this is negative, then I can tell that g alpha minus g0 is less than 0. Anyone has confusion? It means that g alpha is always less than g0, because I have some kind of negative quantity here. And if I will write like this, g alpha less than g0, what does it mean? G0 is not a minimum, because definition of minimum is, one can give in reverse way, that if G0 is the minimum, then you can take any alpha in some ball. Okay, so all value of alpha that should be less than that. Okay, so if you assume g double dash 0 less than 0, then whatever condition for minima, that is no longer true, and due to that reason I am telling that whatever condition I am assume by contradiction, so I am telling that g double dash 0 is greater than 0. Okay, so I hope that you are able to understand this proof. Main idea of proof is like this, that in mathematics I have just two things, either thing is true or false. Okay, So what I have done, if something is true, you can assume the false. And if somehow you are not able to prove false, some contradiction occur, then obviously that is true. Okay. So due to true and false logic, I can able to prove in this way. Anyone has confusion? Okay. Now in this way, I am able to understand that what is the second order necessary condition for optimality. Okay, now what I am going to do, I am going to express g double dash means second order derivative that I have written that is greater than equal to 0. Okay, so I am going to interpret same kind of condition with help of this function. So here basically I have equality sign also. So now what I am going to establish the relationship. Using this relationship, what kind of extra relationship that is going to reflect in terms of f, that I am going to derive now. Okay, so what I have done, again, since I know g alpha is f x star alpha and d, I am going to take two time derivative of this. Okay, so if in the previous class I have seen that if you take the first one time derivative, then that is gradient, and after that I have inner product and d. Okay, now what I am going to do, I am going to take again derivative with respect to alpha two time. Okay, so if you take two time differentiability, then two time partial derivative comes into picture. Please do by yourself, that is not a very difficult job. Okay, and after that you have to substitute alpha equal to 0, because I know that x star is the x star point. Somehow I have to analyze x star point. So how to analyze x star point? If I substitute alpha equal to 0. So due to that reason, this particular expression comes into picture. Okay, whenever I have this kind of expression, it is possible to show that here you can see that ij from 1 to n. So you have to vary I and j both from 1 to n. Then I can also write this whole quantity in terms of matrix representation. Okay, and it is possible to show that matrix representation of the same can be written like this. Okay, where d I have some kind of column vector I have to d to n. Okay, so if you take the transpose, then this become 1 cross n, and this is n cross n, and this is basically n cross 1. Okay, so finally I have some kind of a scalar function only. Okay, and this matrix has some special name that is called Hessian matrix. Okay, I hope that several times you might have encounter with this kind of situation whenever you are taking two time derivative and after that expressing in the matrix form. Okay, so either you can write in this form or this form. This form is basically little more convenient. Okay, and if I will see that this particular matrix df, so df I have actually I have to write like this, d2fx, this whole quantity is like this. Okay, this whole matrix. Now what we have to do, I have to relate g with x, and due to that reason, means in previous slide we have seen that when something is minimum, alpha equal to 0 is the minimum or x equal to x star is the minimum, at that time this condition should be satisfied. Okay, due to that reason I am going to substitute same condition. So you can see that second necessary condition is nothing but this d2f x star, that should be greater than equal to 0. So positive semi definite, because equality is also there. And how to check positive semi definite? What you can do, that either you can check the eigenvalue. If all eigenvalue are the positive, okay, positive or equal to 0 is also allowed, then I can tell that that is positive semi definite. Otherwise what you can do, you can create some kind of element you can check this is positive, after that second determinant is positive and all determinant is positive. Okay, so you can check using the principal minor. Okay, so second, this is the second order optimality condition, and now you are able to understand why I am telling this is second order optimality condition, because this condition comes into picture due to the second order Taylor series expansion. Okay, now what I am going to do, I am going to talk about the sufficient condition. Okay, so actually what happens, I have generated two necessary conditions. Now if I add two necessary conditions, it is possible to show that there exists some kind of sufficient conditions such that some event will occur. Okay, it is possible to show in order to occur of some event, several necessary conditions should satisfy simultaneously, and several necessary conditions produce some kind of the sufficient condition. And why that is only sufficient? Because if these two conditions will hold, okay, so I have actually drive one kind of condition like g dash 0 equal to 0, g double dash 0 that is greater than equal to 0, or in other word that delta f x star that equal to 0 and delta 2 f x star that is greater than equal to 0 corresponding to that. So these two are the sufficient condition. Now what I am going to do, I am going to claim that if these two conditions hold simultaneously, then event is going to occur. Okay, so suppose if these two conditions will not occur, then also it is possible to show that some event may or may not occur. Okay, so due to that, but if this condition occur, then I can give guarantee that event is going to occur. Due to that reason, this is nothing but sufficient condition. But if this condition will not satisfy, one of this condition will not satisfy, then I cannot claim anything. That is the meaning of sufficient condition. But necessary condition, meaning of necessary condition, if this doesn't hold, then I can able to give guarantee that minima is not going to occur. Okay, that is the meaning. Anyone has confusion on necessary and sufficient condition, then please let me know. So somehow several necessary conditions when comes together, then they will form some kind of sufficient condition for the occurrence of the event. Okay, same kind of things actually happens here. Okay, so now theorem, what theorem is suggesting, suppose f, I have to minimize some function, real valued function, where x belongs to Rn. Now what I am assuming that f is two time continuously differentiable. Okay, and if this condition, now what I have done, I have actually keep here the more stronger condition than previous one. Okay, previously second order necessary condition I am assuming greater than equal to 0. Here you can see that I have just considered that is f means Hessian matrix is positive definite. Okay, so on interior point x star of its domain, then x star is a strict local minimum of f. Okay, I have already told you that whenever I am selecting some kind of minimum point or maximum point or extremum point, at that time I have to check that in this some region D, this point value about this point that become least. Okay, so whenever I am talking about the local minimum, a strict local minimum means I hope that this kind of inequality always occur less than fx. Okay, this value should be whenever I am talking about the minima. Okay, so now what I am telling that if these two conditions will satisfy, then I have a strict local minima. Okay, so I have to think about some kind of interior point x star of its domain. So this domain is here, so I have to assume that this is lie inside, not lie on boundary. Okay, if that will lie on the boundary, then we know that it is difficult to define D, this function, because whenever I am solving it, at that time I am defining like f x star alpha and D, and basically this alpha is somehow give us the direction. Okay, so whenever I am choosing the direction, at that time if you are in boundary, it might possible you can leave this space, and due to this region, if you are inside this, then I can give guarantee that after taking this kind of increment, you can tell, or decrement, I can still remains inside the boundary. Okay, so let us prove this theorem. So what I am going to do now, again I am going to express gx in terms fx in terms of g alpha. So that is given like this, and after that now directly I am going to do the Taylor series expansion. Okay, so directly if you write Taylor series expansion, then this expression comes into picture, assuming delta fx star equal to 0. Okay, if you have confusion, then please just see from here that if I have done Taylor series expansion, 2 times Taylor series expansion, then g alpha equal to g0 g dash 0 alpha. So if you see the g0 is nothing that correspond to fx star. This particular quantity that correspond to fx star alpha d. Since this quantity is delta f x star, so if this is 0, then this will not present, and these two quantity we have just seen that I can represent like this Hessian matrix f x star into d, like this, and due to that reason I have written this particular term directly. Okay, like this. Anyone has confusion? And obviously alpha square is involved because I'm talking about Taylor series expansion, and again I have higher order, this is higher order term. Okay, now Hessian matrix delta square fx is positive definite. I am assuming this is positive definite, and alpha square is here, and if that is greater than 0, and if this term is going to dominate over this term, it is possible to show that now fx star alpha d fx star plus some positive number. Okay, and due to that reason I can tell that always this kind of condition is satisfied, that alpha d that is greater than equal to fx star, because I am assuming that that is strictly greater than 0. Anyone has confusion, then please let me know.
Excuse me, sir. Sir, D. What is actually D? Actually, I missed some classes. What is D?
D is basically, suppose that you have function fx, okay, and I am telling x is n dimensional function. Okay, so here I have some kind of vector space where x1 x2 and xn is going to lie, and I am assuming that x belongs to D and D is subset of Rn. So I am in this particular region, and after that now if I identify some point x star, so what is x star? That is x1 x star, x2 x star, something like x3. So this is number. After that I have to check that at this particular point this particular function fx has list value. So how to check? I have to somehow travel in this particular region. So how to travel? First you can define another vector. So I have defined another vector. Okay, and what I have done, I have taken the addition of this quantity plus this alpha might be negative and positive. Okay, so using by varying alpha I can able to travel in whole region. Okay, and here you can see that two things I have defined, that vector addition and scalar multiplication. So I can able to remain in this space, I cannot going to leave this space. Have you understood now?
Okay, sir. Sir, actually, can we write like this? Suppose if we write fx plus h in Taylor series, we write just fx plus h
No,
f.
try to understand here. Actually, whenever I am writing fx plus h, at that time I am assuming that this is a scalar number. Okay,
Okay, sir.
x belongs to R, but here that is not the case. Here x is a column vector. Okay, column vector which has n number of entry. So whatever h I am going to construct, that should be also column vectors with n entry. Otherwise I cannot able to add one vector with one scalar.
Yes, sir.
So basically whatever role of H that is played by alpha plus alpha multiplied by D, because I am in vector space. Okay, so vector space only two operation is possible, vector addition and scalar multiplication. Okay, now I have to travel in whole space. I know this point, and due to that reason I have taken another point from the vector space general point, and after that I am going to multiply alpha, and after that I am going to give guarantee that this point is not going to leave D. Then only I can tell that fx star is the minimum point. Any confusion?
No, sir.
Okay. Now you can see here that I have already told you that this term is going to dominate. This term is less dominant over this term everywhere I am assuming, and due to that reason this kind of relationship comes into picture, that this kind of things comes into picture. Anyone has confusion? Again please see here that I have taken the second order Taylor series expansion. So fx star, because if you interpret in terms of g alpha, this is g0, because most of time whenever people are doing Taylor series expansion, so they are thinking that that they can perform about the zero. Okay, and obviously I have extension that Maclaurin series or these kind of things. I am not going to brought that here. And another is g0 into alpha, after that g0 dot alpha square, something like that. Now what I am going to do, I am going to substitute value each and every value. So here g0 is fx star, g dash 0, because I am assuming that this condition will satisfy, due to that region that is automatically 0, and after that I am going to substitute this. Okay, and this term is actually going to less dominate over this term, so automatically I have fx star plus alpha d, so fx star plus some number, positive number. So if I remove positive number, so left hand side is going to dominate over fx star, and that is nothing but the condition of the strict minima. Anyone has confusion? And due to that reason I am claiming that if delta f x star equal to 0, delta 2 f x star that is greater than 0, then I have a strict minima. A strict minima means if I can take the neighborhood of x star, then always this kind of condition holds. Okay, anyone has confusion, then please let me know. So this fx star has lowest value in that whole local space. Okay, now you can see that whenever I am assuming this kind of things, then I have to make sure that alpha should be very small. Okay, so and I am assuming that direction. Okay, direction I have selected in such a way such that x star alpha d that is going to remains in the same domain. So suppose I have to solve optimization problem like d is the subset of Rn. So I have to make sure that x plus alpha d, x star plus alpha d also should lie in D. Okay, so for this I have two restriction, and what is that two restriction? That this alpha should be a small enough. Okay, and what is meaning of a small enough? I have to make sure that alpha is less than equal to epsilon. Okay, after that whatever vector I have selected D, so after multiplying with this small number, that is going to lie inside this region only, that will not leave this region. Okay, and due to that reason whenever I am talking about these two conditions, at that time I am assuming that this is always hold. If this will not hold, so this is our assumption. Okay, so this kind of theorem is true only when this assumption is satisfied. Okay, and you can see that during theorem where that assumption is reflected, I have written interior point x star of the domain. That kind of things I have written here. Okay, so somehow interior point inside the domain, mathematically I can tell that that is nothing but this whole things. Obviously alpha is less than epsilon. Okay, so a strict minima or local strict minima occur provided that x star plus alpha d that is going to lie inside this region. Okay, now I have to make sure this kind of condition if I wish some kind of strict minima. Okay, so for that, now question is that how to select alpha, how to select d. Okay, it is possible to show that if I am in one dimensional space, then things is pretty easy. I can select one line of unit length and after that I will vary alpha. So alpha I will vary in a small amount. If I am in higher dimensional space, then I have to select some kind of sphere. Okay, and that sphere should be closed and bounded. Okay, then I can able to give guarantee that if I am remain in the vicinity of x star by performing this kind of operation, I am not going to live in this particular region. Okay, so let us try to see next slide, then you are able to understand the situation. So I have to, whenever I am going to talk about a strict local minima, at that time I have to see the feasible direction. Okay, and if you see the feasible direction, it is possible to show that if I have some kind of convex region, then it is possible to give guarantee that this kind of condition will satisfy. So that kind of things I am going to establish now. This kind of condition will satisfy. Okay, you might be remember that during our school time we are not caring about direction or anything. Why? Because we are not bothering about the proof. Okay, we are selecting those kind of function which is very well behaved. Okay, and after that we are just putting these two conditions and checking that there exists a minima. But now we are mature guy, so we have to make sure that all conditions should satisfy. Okay, so obviously these two conditions not always generate the strict local minima. Okay, I need some extra condition also. Okay, and how to actually come up with that extra condition I am going to discuss in this slide. So the key fact that we used in the previous development, that every d x star plus alpha d for alpha sufficiently close to 0 belongs to d. So that kind of things I have used. If I do not assume this, then I cannot able to prove g dot equal to 0, or at the same time this I cannot prove. Okay, because development of this I am assuming that the alpha is positive and negative. So based on alpha negative, I have actually generated this kind of condition by proof of contradiction. Okay, and due to that reason, this direction is very essential. Okay, so suppose if we are at boundary. Okay, so if we are at boundary, then I have two directions. Suppose that here you are and I can move in this direction and this direction. So if I define here x star is lying here, and after that alpha and d. So alpha, if I select positive, then that is okay. Suppose this direction I am telling that is positive alpha, or positive alpha greater than 0. But for negative direction, if I will move, then I can move like this and I will leave that region D. This is some kind of region D. Okay, so if we are at boundary point, then I cannot able to give that even if these two conditions will satisfy, then there occur some kind of minima or not. Okay, and due to that reason, what I have to do, I have to make sure that there exists some kind of feasible direction. Okay, and feasible direction I have to select in such a way such that this condition will hold. Okay, so if I am not able to do, then necessary condition is violated. So now what I am telling, that if suppose that I cannot able to move in this direction, but at least I can move in this direction. So if I will move in this direction, So still you can see that I can able to write G alpha like this. There is no problem. But I have to now what happens that I have to assume that alpha is only greater than 0. Alpha greater than 0, I have assumed that is the feasible direction. Okay, so opposite direction I cannot able to move alpha. Okay, so I cannot able to establish this thing, I have already told you. Okay, so now what I have to do, you can see that again I can relook the expression that G alpha, I can still able to perform the Taylor series expansion because that is two time differentiable. So that is G0 G dash 0 alpha G double dash 0 alpha square, and after that I have some kind of higher order term of order 2. Okay, now you can see that if I assume this is greater than 0 and this is greater than 0, because I cannot assume now G dash 0. Why? Because in order to establish G dash 0 equal to 0, I have requirement is like this: alpha should be positive and negative. Based on that argument only I have proved G dash equal to 0. So now G dash not equal to 0. So I have to make sure that G dash 0 and alpha, okay, so this whole quantity, so actually I am now, you can see that one more thing, that alpha greater than 0. So I have to assume that G dash 0 should be greater than 0. Okay, and whenever I am assuming G dash equal to 0, so G dash I have defined like this: delta F x star and inner product D. So that should be greater than equal to 0. So equality is also fine, that is not a problem, and due to that reason I have written that it is possible to show that x star is still a local minimum provided now this condition for every feasible direction in D, if this condition will satisfy. Anyone has confusion? Have you able to understand this point or not? Since alpha I can take positive and negative, due to that reason I can able to establish this. Now alpha is greater than 0. So if alpha is greater than 0, then I am telling that G alpha, and in order to establish relation between G alpha and G0, so I have to prove this kind of things. G alpha should be always that is greater than G0. That kind of things I have to prove. So it means that whatever quantity that is added to G0, I have to make sure that is positive. Okay, so G double dash alpha square, that is always positive. Now I have to assume that this should be positive. Alpha is already positive, so due to that reason G dash 0 should be greater than 0. Now G dash 0 I am going to express in terms of F, and if you express, then this term comes into picture. Okay, so please come here. It might possible you might forget about the relationship between the G. So I am again back to the first or second slide probably, where we have established this kind of fact. Yeah, here you can see that G dash 0 is delta F x star minus D. Okay, so I have to make sure that this should be greater than equal to 0. Okay, if we are able to do so, then from here let us come to this expression. Okay, so in this expression I have to establish like G alpha that is greater than G0. So how to do that? I have to make sure that all term from here to here that is positive. I know that this is already positive by second order necessary condition. First order necessary condition is violated because now alpha is greater than 0. So G dash should be greater than 0. And this term is already taken care by this term. So that is, there is no need to worry about that. Okay. And due to that reason, whenever I don't have feasible direction, at that time I have to check this. Anyone has confusion, then please let me know again. And after that, so second order necessary condition, that is G double dash 0 is still true if G dash 0, which together G dash equal to 0 and G implies that we must have this kind of things for all feasible direction, and if you do so, then finally again you can land up to this point. Okay, and it is possible to show that if you have convex point, then this kind of things is always true. Okay, so suppose if you have this kind of situation, and suppose this function is defined in this region, and if you move in feasible direction, okay, suppose this direction is only feasible because I am assuming this kind of region, it is possible to show that in this particular place always x star f x star here, this is not a star, and d that is greater than equal to 0. So I can move in this direction and finally I can land up to this point only. Okay, anyone has confusion? So same kind of things I have written. If d is convex, then line segment x star to a arbitrary point x lie entirely in d. So that is the definition of convex region. Whenever something is convex, then what happens, you can take 2 point might be in higher dimensional space, and if you add these 2 points, then actually line joining between these 2 points always lie inside that region only. Okay, and this is the condition. It means that if I move in the feasible direction, then I can able to get the minima, and due to that reason I am assuming that now whatever region d I have considered, that is convex. Okay, so now you are able to understand that whenever I am talking about the extremum means strict minimization in some region D. At that time, I have to make sure that D is convex region. Okay, and after that, whatever two conditions that should be satisfied. Now, if you see the engineering problem, at that time we are worrying about the global minimum over a given domain. We are not just actually concentrated on the local minimum or local strict minimum. We are searching for the global minimum, and we are going to discuss that how basically one can land up to the global minimum if they know the theory of local minimum. Okay, so same kind of things I have written, that typically we are interested in finding a global minimum over a given domain, and again most of time engineering problem whenever we are solving, so this is real valued function, and at that time I have this kind of assumption. Okay, now what I am going to do, I am going to introduce some another theorem, that is wire stress theorem. And what this theorem is telling, that if f is continuous function and d is compact, okay, compact set means closed and bounded set, then there exists a global minimum of f over d. Okay, so those who has done course on nonlinear control, I hope that they are already familiar with the compactness. Those who has not done, please check the meaning of compactness. Please try to see some kind of example that how to define the compact. Okay, compact set or compactness, how to define. Okay, so for simplicity you can think like this. If you have some kind of a space, and whenever I am telling that a space is closed, it means that they will contain some kind of limiting point. What is meaning of limiting point? That if you vary something, then finally you land up to some kind of point. Okay, it means that you are going to converge somewhere, and after that bounded means I am assuming that all point is going to lie from some certain fixed point, and whatever distance that comes into picture, that is fixed. Okay, so suppose if I am assuming this region is compact region, it means that I am telling that okay, some kind of limiting point that exists inside this, and after that all other point is actually d distance from here, or some distance epsilon distance from here. Okay, so epsilon distance that is given by bounded, and closed means there exists a limit point. Okay, so if I have some kind of region like this, and if that function is basically defined in this particular region, it is possible to show that if you define this kind of things, then you are not going to leave this particular region. Okay, and due to that region compactness condition, if that comes into picture, then it is possible to show that that function has a global minima. Okay, and it is possible to show that if you consider some kind of convex function, or convex region, then automatically this kind of things comes into picture after some extra assumption. Okay, there are another definition of compactness I am not going to discuss in this class. Okay, because this required again knowledge of topology or other kind of things, and due to that reason, just you can assume that I have region and I have that region is going to contain some kind of limiting point, and all other point that is going to lie on some fixed distance, then that is called bounded. So containing limiting point, that is called closed, and all point is actually from this point at some kind of fixed distance, that is called bounded. If both things are satisfied, then that is called closed. Okay, anyone has confusion on this intuition? So with help of this intuition, now what is procedure to find the global minima? What I will do, that find all interior point of D, I am going to check this. Okay, so I know that my x is basically defined in this particular region, so I will solve this equation x star equal to 0. Okay, suppose f is not differentiable everywhere. Suppose whenever I am considering this, then I am assuming that f is differentiable, one time differentiable. But suppose somewhere that is not differentiable, that point is called critical point, and it is possible to show that some boundary point or somewhere that is not differentiable, that point, and I have to check about that point also. Okay, and what I have to do, find all boundary point that satisfy this. We know why this condition comes into picture, in order to make sure that I am going to move in feasible direction, and due to that reason, at boundary point, okay, where that is not differentiable, then there I have to make sure, and after that I have to make sure at boundary also that this condition will satisfy. So I have to write algorithm such that whenever we are at boundary, then I can move in some kind of feasible direction. I will not going to leave the boundary, otherwise I cannot able to find the global minima of this region D. Okay, finally compare all these value and choose the smallest. Okay, and if second derivative will also exist, okay, you have some kind of algorithm to find second derivative, then move in that particular direction also and combine with the first one. In this way we are solving the global minimization problem, and this problem is tractable provided I have already told you that if D is convex set and f is a convex function. Okay, so if fx is a convex function and D is a convex set or some kind of compact set, it is possible to show that automatically there exists a global one. Now you can see that one more condition, because if you are f double dash x greater than 0, it is possible to show that f function is convex. Okay, and if D is convex and at boundary, if I will check this kind of condition in feasible direction, it is possible to show that finally I will converge here only. Okay, and since first order necessary condition is also a sufficient condition here, this is sufficient condition, because what happens that, why I am telling just sufficient condition, because I cannot establish now this kind of things everywhere. Okay, but at least I can establish this kind of things whenever I don't have feasible condition, and due to that reason I have written this as a now necessary condition as a sufficient condition. Okay, sufficient condition means now even if this will not hold, then also I have possibility of minimum. Okay, and why that is global one, because whenever I have convex function, so convex function can be written like this. Okay, and here I know that delta fx and x minus x star you can define as a D, so that is greater than 0, and due to that reason I can tell that always I can move towards the global minimum point. Okay, and all algorithm steepness decrescent or gradient method is basically based on this idea only. I have convex region and convex function, and then we are going to find the global minimum. Okay, so now it is time to conclude the today's lecture. So what we have seen in today's lecture, that whenever I have to solve unconstrained optimization problem, so apart from two necessary conditions, and I am going to restrict the second necessary condition, then that will not always give the strict local minima or global minima. So for that I need extra condition. Okay, and what kind of extra condition is required? Either that D should be compact. If D is compact, then I can able to, at least I can able to make sure that if I have some kind of boundary, and at boundary point, if I move in feasible direction like delta F star D that is greater than equal to 0, then finally I land up to the local minimum. Okay, and if F is convex as well as region is also convex, then it is possible to show that there exists a global minima. Okay, and based on that all algorithm has created. So what is main motivation to discuss this proof? What we have observed that in this particular proof, that apart from the two condition, okay, two sufficient condition, two necessary condition, I have to also take care about the direction whenever I am solving the optimization problem. Okay, during a school time, basically we are not bothered about that, because we are assuming that whatever region that is convex, whatever function that is also convex. Okay, and then we are talking about the minimization problem. But now we are very much mature, so we have to understand each and every point. Okay, so now in next class I am going to talk about the unconstrained optimization problem, constrained optimization problem. Unconstrained I have already did for finite dimension, so I will deal constraint for the finite dimension. Okay, and obviously we can move then the constraint and unconstrained for infinite dimension. Okay, and in whole optimal control course I am going to talk about the infinite dimensional optimization problem only. But if you have some sufficient background of finite dimensional optimization problem, then easily you are able to understand the infinite dimensional problem too. Okay, so if now lecture is in from my side, if you have any questions, then please let me know. So thank you very much if you don't have any question.